It's finally time to learn how stoichiometry works, and we're going to do it in a really quick and easy way. This equation tells us how we can create water. You take some hydrogen gas and you take some oxygen gas and you burn the hydrogen in the presence of oxygen and you actually create water. Now, if we were to write out the molecular representations of it, we see that hydrogen is diatomic. It's one of the diatomic elements. Oxygen is also a diatomic element, so every O2 molecule is two oxygen atoms bonded together like this. But we can see that this is not balanced because if we draw one water molecule, so I'm going to take one of these, I'm going to duplicate it. If we take one water molecule, we'll see that it's not balanced in terms of where the atoms are. How in the world can two hydrogen atoms become two hydrogen atoms? Okay, so far so good. They split and move around. But how can two oxygen atoms become just one oxygen atom? In order to make this equation make sense initially, we must balance the equation. You cannot change the subscripts, which are the little numbers, because that would change the substance. For example, if I decided to just make a 2 here, and now it's, H2 plus O2 gives us H2O2, that's no longer water, that's hydrogen peroxide, a completely different substance. You cannot change the subscripts, but you can change the coefficients to get that ratio correct. So to do that, I'm going to try to balance this out, and I'm going to show you what it looks like in the molecular representation. So I'm going to make another water molecule. Suddenly that fixes the oxygen issue, correct? I can put a 2 here for the coefficient in front of water, because now I have 2 moles of water, 2 little packages of water molecules. Over on the other side, we now have a balanced number of oxygens, but our hydrogen number is unbalanced. So I can't just take away or add any more little white ones in terms of to that same molecule, but I can create more of those molecules. And now we have a balanced number of hydrogens. I have to change my ratio up here, but we can see here that 2 moles of hydrogen gas, so 1, 2, just 1 mole of oxygen gas, that's the recipe to create water in a 2-1-2 ratio. You don't typically put the 1 in an equation, but I'll put it here just so you can explicitly see where it is. But just like in math class, you don't need to put a 1. All right, so now we have a balanced equation, which is the first step of stoichiometry. Let's take a look at the first question. How many moles of oxygen are used to create 12 moles of water? Notice how the word hydrogen is not mentioned in the first question, and that's okay. If a particular substance is not mentioned, you don't worry about it. So how many moles of oxygen are used to create 12 moles of water? Here's how this problem is going to work. I take what I know, which is 12 moles of H2O. So that's this. And I like to put everything over 1, optional but recommended. And now I look at my units, moles of H2O, and I'm going to put that in the denominator. I'm going to go from moles of H2O toward what it's actually asking about, which is moles of oxygen. So I'm going to put moles of O2. Now I can look at my moles of water, cancel out top and bottom, circle moles of oxygen. I highly recommend that you put your units and substances down first, like I just did, and then you can add your coefficients, which is your ratio. This is called the molar ratio. So when you use these big numbers, you're using the molar ratio. And we're about to do that here in this dimensional analysis. Because when you have 2 different substances stacked on top of each other, so we're transitioning from water to oxygen in terms of knowing things, you're going to use the molar ratio and put it there. So what are our ratios for this? The molar ratio is a 2 next to the moles of water and a 1 next to the moles of oxygen. And that's actually it for this question. Because from this, we're going to get 12 moles of water, and if you divide that by 2, we get 6 moles of oxygen as your answer. So this kind of makes sense. If we make 12 moles of water, 1 mole of oxygen can give us 2 moles of water. So we only need half the number of moles. And that's coming straight from the molar ratio. We weren't even worried about hydrogen. We assume that the hydrogen's unlimited or in excess. So this right here is an example of a molar ratio or a mole-to-mole conversion. But one thing you've got to understand in chemistry is that moles are like the main currency you can get into and out of a mole. You can use molar mass to convert grams to moles or moles to grams. And we're going to do that here. Question 2, how many grams of oxygen are needed to make 65 grams of water? So at first, we were asked about moles and moles. It's only one more step to do grams and grams. So we know one thing, and that's that we have 65 grams of H2O over 1. I'm going to go from grams of H2O to moles of H2O. you're going to need a conversion factor here. So how in the world do you go from grams of H2O to moles of H2O? What's that special link? You need to review how to calculate molar mass, but I will tell you that the molar mass of water is about 18.0. That basically says that if you have 1 mole of water, which is 6.02 times 10 to the 23rd, if you have 1 mole of water, it'll weigh 18 grams. So this right here, this ratio, is the molar mass ratio. That's an important one to note, that when you go from grams to moles, or from moles to grams, you're going to use the molar mass. But we're not done, because if we were to stop the problem here, all we would have done was convert grams to moles. So we would have found out how many moles of water 65 grams of water is. We actually got to go a couple more steps. So let's continue our dimensional analysis. We have moles of H2O in the numerator because it hasn't been canceled, so we're going to put that in the denominator. And this is where we transition from one substance to the other substance. I'm going to go from moles of H2O to moles of O2, which is oxygen. And just like we did in the first question, we're going to use the molar ratio. So this is the molar ratio. The molar ratio is going to come from the balanced equation. Sometimes you'll be given an equation and it's not balanced, but we actually took the time to balance it, which means we put the correct coefficients. So what are those coefficients? Same idea, it's a 2 next to the H2O because that's what's here. And there's a 1 next to O2 and that's what's here. Now we can cancel out moles of H2O. And if we were to stop the problem now, which would be a valid stoichiometry problem, we will have simply found the moles of oxygen. But it's more common to talk about the grams of oxygen, for example, or sometimes liters, but that's a different video. So let's go another step. And we're going to put moles of H2 or moles of O2 in the denominator. And we're going to go from moles of O2 to grams of O2. Notice something similar. Although we're dealing with O2 instead of H2O in this part of the question, so later down the problem, we still have a ratio of moles and grams we need to use. So in this case, we had moles over grams, and now we have grams over moles. It doesn't even matter where the moles and the grams are, because you've got to see that moles and grams, when they're touching each other on opposite sides of this fraction bar, think of molar mass. Molar mass. Molar mass. What is the molar mass of oxygen? If you look on the periodic table, you'll see that a single oxygen atom has an average atomic mass of 16.0. But since this is O2, so notice how this is not just a single oxygen atom, but it's 2 oxygen atoms. It's the 16 on the periodic table plus another 16. So the molar mass of a diatomic element is literally the atomic mass times 2. So on the periodic table, we would see that it's about 32.0 grams for every 1 mole. We're going to cross out moles of oxygen, and are we actually at where we need to be? It asks, how many grams of oxygen? Perfect, because we have grams of oxygen as our surviving unit. And at this point, we can do our math to figure out what it is. So it would be 65 times 1 times 1 times 32. And we would divide that by 18 times 2. And we would get an answer of about altogether, I should say, around 57.8 grams of oxygen. So what we did when we answered this question is, we answered the question, how much oxygen effectively is consumed when we create 65 grams of water? We didn't even concern ourselves with the hydrogen, because just like with the first question, we're assuming hydrogen's in excess. So we don't need to concern ourselves with it. That's how stoichiometry works. You'll use moles. You'll sometimes start with moles and end with moles like we did here. But oftentimes you will, as you progress further in the course, you will start with grams or volume or number of particles, and then you'll end up with grams or volume or number of particles. The main takeaway here is that you are always going to either start with it, end with moles, or you're going to go through the mole. Notice how in question 2, the word mole wasn't even mentioned. You just got to train your brain to think that when you do stoichiometry, you're going to use molar ratios from the balanced equation, and you're oftentimes going to use the molar mass or some other additional ratio or conversion factor if you need to go beyond the mole. In this case, we used molar mass to convert grams to moles to mole ratio using the balanced equation, and then moles to grams again using a different molar mass. Let's do 2 more stoichiometry problems. Sometimes they're worded a little differently, so these are worded in a way that you also might see. Number 3 says, what mass of water can be created from 236 grams of hydrogen? So we have available to us 236 grams of H2. And I'm going to go from grams of H2 to moles of H2. Whenever you have grams or something given to you, just immediately think, how can I get this into moles? To get grams into moles, you got to use the molar mass. So which molar mass are we going to use? The one for hydrogen. So if we look on the periodic table, we'll see that the average atomic mass for hydrogen is about 1.01. But since it's H2, we got to double it. So it's about 2.02 or so. So we can put that 1 mole of hydrogen has a mass of about 2.02 grams. That cancels out grams of hydrogen, and if we were to stop the problem here, we would have simply done a grams to moles conversion for hydrogen. It doesn't answer the question about water at all so far. So we got to keep going. Multiplication symbol, fraction bar. Look at the unit we currently have, which is moles of hydrogen. And we're going to put moles of hydrogen in the denominator because we want it to go away. Ultimately, we're asked about mass of water. We're asked how much water can we create given this much hydrogen. Don't even worry about oxygen. It's not even in the question. It still exists. It's still necessary to make water, of course. But since oxygen is not mentioned, don't think about it. So moles of H2 to moles of H2O. I'm actually going to switch colors so it's a little bit clearer. Moles of H2 to moles of H2O. At this point, we're switching substances. We're going from H2 to H2O. So what do we do here? When you have moles of something over moles of something else, so moles of whatever over moles of something else, you've got to use the molar ratio. Now, the good thing about this equation is that it's a 2-to-2 ratio for hydrogen and water. So we can put a 2 for H2 because it's right here. And we can put a 2 for H2O because it's right there. We can cancel out our moles of H2, so they're gone. And if the problem had asked for, so let's pretend like the problem said, what mole? Well, it would say how many moles, but if the problem said how many moles of water, you would stop here. It doesn't ask for moles of water, it asks for the mass of water. So you must convert your moles of water into mass for water. So I'm going to put this here, put moles of H2O in the denominator, and we're going to put grams of H2O in the numerator because that's what we're going toward. Moles of H2O cancel, grams of H2O don't. Verify that you're actually getting toward what it's asking. It does ask what mass of water. So that is a unit that has not been sliced out by the others. That's great. Now we just need to figure out what we put in that space. Here, we're also going to use molar mass again, but we're going to use a different molar mass. Which molar mass are we going to use? Notice how it's the relationship between mass and moles for water. It's just water in this little conversion factor. So we have grams and moles touching each other on opposite sides of the fraction bar. Got to use the molar mass. The molar mass for water is 1 mole of water has a mass of about 18.0 grams. When you do your math, you will get the correct answer. So let's see what that is. About 2,100, I'm just going to round, 2,100 grams of H2O. So this is how stoichiometry works when you have to go from grams to grams. And notice again how we didn't even mention oxygen in the question, so we didn't need to use oxygen in our math. Of course, it definitely still exists, so you can't just get rid of it. And let's do one more. What mass of oxygen is consumed when 87 grams of hydrogen is burned? So again, the word water isn't even mentioned in this problem, but just naturally, when you burn hydrogen in the presence of oxygen, it will make water, but we don't need to actually use water in our math here. We're only going to concern ourselves with H2 and O2. So let's jump into it. 87 grams of H2, so I'm going to put that here, 87.0 grams of H2. And I'm going to get rid of grams of H2 and put moles of H2. At this point, you're probably seeing we have grams and moles of the same substance, so we're going to use the molar mass. And the molar mass of a substance is not going to change based on the problem. Hydrogen, H2 hydrogen, will always have the same molar mass, just like we used up top. So let's use the molar mass here. 1 mole of H2 has a mass of 2.02 grams approximately. We cancel out grams of H2 and we keep it moving. We don't want moles of H2. We actually want to go from moles of H2 to moles of. Always pause and ask yourself, what do I put here? Do I put H2? Do I put O2? Do I put H2O? When you have moles of the starting material, so we started with moles of H2, and you're like, I need to get out of hydrogen. It's giving us hydrogen, we need to get out of hydrogen. And you're going toward moles of something else. You got to think about what goes there. In this case, it's going to be oxygen. Water's not mentioned, so we're going to use oxygen here. So I'm going to put moles of O2. We can use our molar ratio So our molar ratio, just like we saw up here, we used a molar ratio here. I didn't mark it, but I will now. The molar ratio is the big numbers from the equation. So here we're going to use the molar ratio again. You got to make sure you use the right numbers. So because we're dealing with oxygen and hydrogen, we're going to use a big 1 and a big 2. We don't need to worry about water. It's not even asked for in the question. You can cancel out your moles of hydrogen. And we're actually there. Once you get moles of what it's asking for, you really are almost done. So we are currently in the moles of oxygen part of our problem, and we need mass of oxygen. So how do you go from moles of something to grams of that same something? Put it in the denominator. So we're going to get rid of moles of oxygen by putting it down here. And we're going to go from moles of oxygen to grams of oxygen using oxygen's molar mass. One single oxygen atom has a mass of 16.0 approximately, which is why 2 moles of oxygen, so we're going to use the molar mass here. So molar mass, which molar mass? That would be the one for oxygen. Because we're talking about O2, we know that 1 mole of O2 has a mass of about 32.0 grams. Canceling out your units will be really helpful for keeping track of what's going on. So we're canceling out moles of oxygen top and bottom. I like to circle the one that I am needing because that tells me I can stop. It asks for mass of O2. Grams of oxygen is the way you express the mass of O2. And at this point, you can just do your math to get the number. So if we were to light 87 grams of hydrogen on fire, how much oxygen will it pull from the air? It'll pull approximately 689 grams of oxygen from the air. And that's how stoichiometry works.